Hello and thank you all for coming today. As evidently, my name is Marina. I'm just starting here as a professor here at the University of North Florida, so it's very nice to be here. So today we will talk a bit about what star clusters are. So here is, wait a second. Here is an image of what a star cluster looks like. As you can see, it's a collection of many stars packed together in a small volume of space. If you think about our solar neighborhood, then the closest star to us is located, other than the sun, obviously, is located approximately 1 parsec or approximately 3 light years away. Now, these star clusters, they have a total radius of maybe 1 parsec or even less. So you have hundreds and thousands more stars packed in a very narrow volume of space. And stars don't really get there by random. They wouldn't just wander off into a cluster and stay there. Rather, in order to be there, the stars had to form this way. And oh, come on. So how do stars form? It happens within large clouds of gas. And these clouds are so massive, they begin collapsing under their own weight. And in the process, this collapse will eventually form stars. Well, most of these stars wouldn't necessarily stay in this place. Most of these stars would wander off and populate the galaxy. But in the process, you might have a slightly denser spot in this cloud that will go on to form a star cluster. That is to say, all of the stars in a given cluster have formed together at more or less the same time. And herein lies a very wonderful property of these clusters, is that they allow us to estimate stellar ages. Now, normally, if you were to go out and pick a random star in the sky, chances are you wouldn't know how old it is. Certainly not with any degree of precision. And if you were to go outside and just meet a random passerby on the street or look around you, chances are you wouldn't necessarily be able to figure out everyone's ages. Now, if you have little kids, toddlers, infants, you can probably correlate their height with their age. If you have a person with a head full of white hair, you can probably figure out that this person is somewhat older, but anything in between is very hard to determine. And it's the same thing with stars. We can figure out the ages of the stars that are very young. We can figure out the ages of the stars that are very old, but anything in between is quite difficult. And unlike with people where we can just take a picture of each of every one of us and figure out something about us, when talking about stars, we use this diagram. This is one of the most fundamental diagrams in astronomy. Here we have temperature versus the brightness of a star. And here we in the temperature, we have, by rather silly convention, on this end, we have very cool stars. And on this end, we have very hot stars. And for the brightness, here we have very faint stars. And here you have very bright stars. And as might be apparent looking at this diagram, most stars tend to lie on a very narrow strip right over here. This is known as the main sequence. Now, the stars don't move along the main sequence, rather they are ordered on it according to their mass. So that very low mass stars tend to be very cool and very faint, and high mass stars tend to be very bright and very hot. And you can think of these main sequence stars as adults. They go to work and do their taxes. And for these main sequence stars, it is generally very hard for us to determine their ages. But the star, because right over here, the stars are able to regulate themselves. They are able to regulate how big they are based on their mass. But if the stars get very old or very young, they would be found off of the main sequence somewhere over here. So generally here you would have very old stars, and generally here you would have extremely young stars. But not all main sequence stars are made equal. Very massive stars, they live very hard, and they die very young. So these high mass stars have incredibly short lifetimes. They wouldn't stay around for more than a few millions of years because their brightness comes at a cost. So if you see a very high mass stars, you would know that the star would have to be pretty young, because you wouldn't see a very old massive star, because again, they just don't live that long. On the other hand, these low mass stars, they have lifetimes that are longer than the age of the universe. That is to say, every single low mass star that have formed since the beginning of time is still around in our galaxy to this very day. And stars continue on to form, so we wouldn't be able to determine the ages of the low mass stars. So that is pretty much it when it comes to the stars that are found in the solar neighborhood. This is kind of their average distribution. But if you were to take a look at the stars in a given cluster, and remember, all the stars within a given cluster have formed at exactly the same time, you'll find that it's slightly different. If you were to take a look at this diagram of relating temperature and brightness of the stars in a cluster, you'll find that the clusters that have only just formed, you will have a collection of stars of all the different masses. And all of the very massive stars are still going to be around because this cluster has only just formed. But the low mass stars wouldn't quite reach the main sequence yet. They haven't figured out how to regulate their sizes quite yet. As you get towards the older and older regions, the low mass stars will get closer to the main sequence. High mass stars would incrementally begin to die off. And then more and more massive stars will exit the main sequence. They would just burn themselves out after they reach a certain age. So by looking at this diagram, we are able to figure out how old a cluster is, and by the extension, how old all of the stars in that cluster are, because all of them have formed at the same time. So there are two different types of clusters. There are open clusters and there are globular clusters. And just by looking at them, looking at these two representative examples, what are some of the differences that are immediately obvious looking at them? Yes?
The open one is like the stars are together close.
Yes.
The open one is closer together.
Yep, exactly. So here, these stars are a bit more widely dispersed, and these are a bit more compact. Anything else? Yes?
They're younger,
Yes. How do they know?
and they're a lot closer to us in our galaxy.
Yeah. Well, I mean, here, look by looking at their colors. Here, the open clusters tend to appear to have a lot of blue stars. Blue stars are very massive and very bright. They outshine all of the red stars combined, because you still have a lot of low mass red stars in this cluster as well, but they're just not quite as apparent. On the other hand, here in a globular cluster, all of the high mass stars have long since died off. So all you're left with are these very old, faint red stars, but you have a lot of them. So the primary two differences are their color and their morphology. And morphology is also can be attributed to their age, because when these clusters only just form, they tend to have very irregular shapes. But as the stars orbit around the cluster many times, they will eventually have a much more regular spherical globular appearance. As different that is slightly less obvious is their mass. So these open clusters tend to have anywhere from a few hundred to a few thousands of stars. these global clusters are orders of magnitude more massive. They tend to have anywhere from tens of thousands to millions of stars within them. So quite a significant difference in mass. And as was mentioned, they have very different ages. Open clusters, you generally have ages of a few hundred millions of years. On the other hand, global clusters tend to be incredibly old. They have ages of several billions of years. In fact, they have ages very close to the age of the universe, acting as great benchmarks of what the age of the universe should be. And so looking at these numbers, you might wonder, well, did our galaxy, was it able to form clusters very early on, and then it stopped forming clusters, and then it suddenly started forming clusters again 2 billions of years ago? Well, no, clusters are a consequence of star formation. Whenever you form stars, you would form star clusters along the way. But these clusters, we tend to think of them as gravitationally bound, but they're still able to disperse stars along the way. At one point in time, one of the stars would pass by something that it has encountered and would gently drift away from the cluster. Then another star, then a third one, and so on and so forth, until eventually these clusters just completely dissolve and populate out the galaxy. So most likely, our sun has formed inside a cluster similar to this one, but we have no idea where are any of the solar siblings are. They could be anywhere throughout the galaxy by this point in time. So why did global clusters stay together? Well, they were forming very early on in the formation of our galaxy, and the conditions back then were just incredibly different compared to what they are right now. So there used to be much more gas that was available to form stars. And probably the galaxy was slightly more efficient in converting that gas to stars as well. So these global clusters, they began their lives as incredibly massive entities. And so they had much more stars they could lose before they would fully dissolve. But also they are able to hold onto the stars so much more tighter because they are much more massive. So that's why we have this slight discrepancy. We have clusters that are incredibly old and the clusters that are fairly young with very little in between, because everything in between that has formed at one point in time has since dissolved. So there's also another difference of where these clusters are in our galaxy. Now, our galaxy is a spiral one. That is to say, it's flat as a pancake. This is a kind of a face-on artistic conception of what our galaxy looks like with the spiral arms. But we can't really see it like this because we are located inside of the galaxy. We are looking at it edge on. What we see is just a narrow strip of light that is forming the Milky Way. And we see that narrow strip because, again, our galaxy is very flat. We're seeing the edge of the disk where most of the stars are. Most of the stars are found in the disk of spiral galaxies. You do have some stars on the outskirts in the halo, but it is a much smaller fraction of them. So where do you think clusters live? Do they live in the disk or in the halo?
The halo.
It's actually both. So if we were to look at here, we see basically this is a sky plot, and right over here we have the plane of our galaxy. And in red are all the open clusters, and in blue are all the global clusters. So you can see that the open clusters are preferentially found in the plane of the galaxy, because that is where you have the most gas. That is where you are forming stars. So open clusters, being very young, tend to be where stars tend to form. On the other hand, global clusters tend to be distributed throughout the halo. They are spherically distributed around the center of our galaxy. And in fact, they were instrumental in us being able to determine just how far away we are from the center of the galaxy, which ends up being approximately 28,000 light years, which is a fairly sizable amount. And 100 years ago, keep in mind that we didn't even know what galaxies were. We would see these faint smudges that were called spiral nebulae, and we had no idea whether they're very similar to the Milky Way, whether something else entirely. So globular clusters were a key point in us being able to determine our place in the universe. Not to be outdone, open clusters also play an incredibly vital role in being able to determine the properties of our galaxy. Because remember, these open clusters tend to live where stars just form. Milky Way is a spiral galaxy. Here we have all the various different spiral arms. And within these spiral arms is where you tend to have the most molecular gas. This is where you are forming stars. And so if we were to look at our galaxy face down, here we have the sun is right over here. Galactic center is towards the right of this image. And here we have different spiral arm. The Perseus arm, the local arm, Sagittarius arm, Norma. So this is kind of the conception of where the spiral arms are in our solar neighborhood. And looking at just the youngest clusters, younger than approximately 100 millions of years, you can see that they're not located randomly. They tend to trace the spiral arms pretty well. Because once again, these clusters have formed inside these spiral arms, and they haven't been able to drift away because they're still so young. So both of these clusters, both open and globular clusters, they allow us to determine not only what the properties of the individual stars are, and how they evolve over time, not just how the clusters evolve over time, but also how does the galaxy function. So that makes them ideal astrophysical laboratories. So looking at this plot, we obviously can't look at our galaxy face down like this is plotted. So there is a critical thing that we are missing in order to be able to make this. And that is to say, we need to figure out how far away all of these clusters are. We need to measure distances towards them. And there are a couple of different ways of measuring distances, but one of the best ones is stellar parallax. Now, I want you to hold your finger right in front of you, like this, and close one eye. And then open it and close another eye, and just blink back and forth. So what is happening to your perception of the finger? It's moving, and if you hold the finger closer, it's going to move even more. And so this effect is referred to as parallax. This is what allows us to perceive distances. This is exactly why we have two eyes. And the same thing is happening with the stars as well. The Earth is orbiting around the sun, and over this period of time, the positions of the stars that are closer to us is going to shift relative to the stars that are much more distant. And the closer the star are, the more they're going to move. The further away they are, the less they're going to move. So the parallax is inversely dependent on the distance towards all these stars. Plus, stars have some intrinsic motion of their own, even so it is incredibly tiny. So over a course of several years, you will see the star wiggle kind of like this. So here you have the intrinsic motion of the star itself, and here you have the motion due to the parallax. And this motion is again incredibly tiny. In order, the parallax to the closest star in the around the sun is going to be on the order of 1 arcsecond. Just how small 1 arcsecond is, there are 360 degrees in a circle, and 1 arcsecond is 1/3600th of that. So pretty tiny, and that is the closest star to us. The further out you go, the smaller the parallax is going to be. And remember, the center of our galaxy is located 28,000 light years away, or approximately 8,500 parsecs away. So in order to measure these angles with necessary precision, to be able to actually see what is happening there, you need to be able to measure angles in the sky that are as small as the size of a dime on the surface of the moon. So that's incredibly tiny. And until recently, we haven't really been able to do that with any degree of precision. But recently, we have had a wondrous Gaia Space Observatory that has been launched by the European Space Agency. And what Gaia does incredibly well is measure minute angles on the sky with incredible precision, thus allowing us to measure parallaxes and motions of the stars in the plane of the sky. And that have revolutionized how we do galactic astronomy literally overnight since it made these data available. So if you imagine this were to be our Milky Way galaxy, we would be roughly over here, approximately 2/3 away from the center of it. And this yellow dot is the size of our galaxy that we have been able to map prior to Gaia directly using the parallax. This red circle is what we have been able to accomplish, what we were able to reach after Gaia first released its data. And this green circle is roughly where we are right now. So we are able to actually see the structure of our galaxy, across the bulk of the galaxy directly using parallax with Gaia. So that changed a lot of things for many fields in astronomy, but where it made the biggest difference is in our understanding of star clusters. Because in the past, how would people search for clusters? Well, you would look at the distribution of all of the stars, and you will try to find where you have a slightly greater density of them. Now, not all of these stars are going to be associated with these clusters. Most of them are in the background or the foreground, having no relation to them. But if you're lucky, you might be able to see the cluster sequence on this brightness temperature diagram. And you might try to isolate them somehow, try to clean it up. But it wasn't terribly precise. But the reason why clusters stay together is because all of the stars are found in a very narrow volume of space, and they're all moving with roughly the same speed, because otherwise they would drift apart. So by looking at what are the velocities of all of the stars in the plane of the sky, and by looking at the distribution of distances for all these stars, you can see that here we have a very tight clump of all of the stars that have very similar motions that correspond to this cluster. And also you have this bump that corresponds to the distance of this cluster. So just by selecting things in this velocity space, we can get a very clean selection of all of the stars that are associated with this cluster. So that allowed us to have much better samples to work with. Not only that, the clusters no longer need to look like this. They can also look like this. That is to say, even so we don't necessarily see a cluster here with the naked eye across all of these stars, we know that there is actually a star cluster there because all of the stars are moving with the same speed in the same direction. So the number of stars that we needed to use in order to find these clusters have dropped significantly. So that have led to a star cluster revolution where many groups of people have started searching for them across the entire sky. Here is a figure from just one study where in red you can see all of the star clusters that have been known prior to Gaia. Here, so once again, the sun is located at the center of this plot. So the center is to the right once again. And all of these blue dots is just what one of these studies have been able to find in terms of all of these new clusters. So their number has increased by several times compared to what we have known previously. And in fact, this has led to some confusion what these clusters actually are and how we would be able to, what will be the minimum size that the clusters need to have in order to be called star clusters as opposed to have be anything else. And personally, I come to this from study of star formation. I am very interested about the earliest stages of stellar lives. And my favorite region of the sky is the constellation of Orion. So here you have the head of Orion, his shoulders, the belt, the sword, the knees. And the reason why I like this constellation so much is because it has a lot of very young stars. You might have seen Orion Nebula before. Without any bias whatsoever, it's probably one of the prettiest places on the sky to look at that is very prominent in the winter skies. It's still a bit too early for it, but be sure to come back in January, February. You'll probably will be able to see it. And the Orion Nebula is an incredibly massive young cluster that is still just in the process of being born. But it is just a tip of the iceberg, because the entire constellation is actually filled with young stars. And if you were to take a look at this outline, this is where you still have a lot of molecular gas that is still in the process of forming stars. So looking at the distribution of all of these stars, you can see they're not here and there along the way. And you might want to refer to them as clusters in their own right. And there is some debate about would you call them clusters or not. So you can continue subdivide it into smaller and smaller and smaller bits until the word cluster loses all of its meaning, or you can go the other way. You can try to trace out the largest possible structure that still appears to be coherent. And as you can see, here are all of the young stars that are associated with this star-forming region. You are able to fill the entire constellation. In fact, the reason why this constellation is so prominent is because it's full of these young stars that are maybe not siblings, but at least they are first cousins. And they're all are moving in roughly the same direction because they have formed from the same cloud of gas that initially had to be very still in order to be able to form stars. So these stars would be able to, even though they are not gravitationally bound, they would be able to move in the same direction for a very long period of time, for several tens, if not hundreds of millions of years. And we would still be able to look at this region of the sky and still be able to see that there's something that have formed together. And Orion, it's very, very precious to me, but it's by far not a unique star-forming region. They all look similar to this. They all have a lot of stars that are distributed across a very large volume of space, but they're all moving in the same direction. So by this logic, we shouldn't really expect these clusters, or certainly at least not open clusters, to be fully isolated. We should expect to find other stuff around them found within these moving groups, where all of these stars are moving in the same direction, even so they aren't necessarily held together by gravity. So this is precisely what we have tried to do. We have searched for all of these different moving groups with Gaia. And here is some of the results that we have had. In yellow, you can see the distribution of previously known open clusters. And in blue are all of the other stars that we have been able to group together in these moving groups. In total, we have been able to group together approximately millions of stars into more than 8,000 of these populations. And the nice thing about them is, just like clusters, all the stars within them have formed more or less at the same time. Therefore, we are able to determine the ages of them. And so here you can see how the youngest populations that are in red, they have very young ages. They have all of the stars on the main sequence, with the lowest mass stars being off of the main sequence. And as they get older, all the low mass stars settle onto the main sequence, and eventually the high mass stars begin to die off in increasingly larger numbers. So through this, we are able to estimate ages of an unprecedented number of stars across the solar neighborhood. And if we were to look at them, now this is a fairly busy diagram that I won't go into too much detail what it is. This is basically the position of the stars in the plane of the sky. This is their distance. And here you have various velocity components. And looking at them in the plane of the sky, you can see they tend to be not isolated cluster-like, but they tend to have a structure of these long extended strings of stars that are, once again, are all moving in the same direction. They have all formed together from the same molecular cloud, and this shape does in fact mirror the shape of the clouds from which stars typically form. So through this, we have been able to connect the study of the youngest stars with the study of the stars for which we have been able to measure ages in clusters. And this is just looking at everything in 2D. We can also take a look at the distribution in 3D. Here's once again, the sun is located right over here. The center of the galaxy is this way. We have all the various spiral arms. And all of these strings of stars have been traced along their spine and placed in this box. And their orientation is not precisely random. They are oriented in parallel to one another, perpendicular to whatever spiral arms they're found next to. So here you can see here they're bunch out in parallel, and here and here. So this has some implications about, well, how do these clouds of gas actually get assembled before they are able to form stars? We don't know the precise processes, but if we were to look at the other galaxies with high resolution, we tend to see these gaseous feathers protruding away from the spiral arms. So this could be the dominant form of why we have all the subcomponent regions arranged in this specific manner. And more than that, it allows us a view into the galaxy as it once was. It allows us to perform galactic archaeology. Because if we're to look at the youngest populations that are younger than approximately 50 millions of years, once again, these populations tend to follow the spiral arms incredibly well. But at the older ages, you no longer see them along the spiral arms. Rather, if you look carefully, you might be able to spot overdensity right over here, and two overdensities right over here and here. So these may be a windows of how our galaxy has looked like when these stars were only just forming, because these overdensities may correspond to the spiral arms as they have existed back then, with all these populations still not fully migrating away from their birth sites. So to bring this to a close, star clusters are very valuable stellar laboratories that allow us to probe properties of the stars and the properties of the galaxy and everything in between. And in the last 10 years, we have been able to progress significantly in being able to determine the ages of stars by searching for more and more and more clustered structures throughout their galaxy. And in the future, in the next 10 years, we are hoping to expand the sample even further by looking at the properties of all of these stars. Thank you so much. Any questions?
What's your favorite cluster? Globular cluster.
Oh, globular clusters. I'm not quite as familiar with globular clusters, but my favorite open clusters is obviously Orion Nebula. Yes?
Do globular clusters lead to black holes?
They certainly, whenever you have star clusters, you should expect there to have been a lot of massive stars at one point in time. And whenever massive stars die off, they do produce black holes in them. So in the open clusters and in the globular clusters, you should expect to have a fair number of black holes. Now, globular clusters may or may not have these mysterious class of black holes that are called intermediate mass black holes that are larger than regular black holes that are formed by exudations of massive stars, but they're smaller than black holes that live in the center of the galaxy. So I think there's a debate still going on that front, but certainly they do have black holes. Yes?
Since the deployment of Gaia, there's obviously been a large growth of discovered stars. When do you expect to, I guess, reach all of the galaxy?
It's a difficult question because Gaia is operating in optical light, as to say the same wavelength of light that we are using in order to be able to see. And our galaxy has a lot of dust along the line of sight. So at a certain point in time, the stars will get too faint for us to be able to probe. There have been some talks about a survey like Gaia, but in infrared, where we would be able to see through the galaxy a bit better, but it won't happen anytime soon, probably in the 50s, if done. Yeah.
So when you're showing the slide about comparing open clusters and globular clusters, I was wondering why the open clusters have so much less mass than the globular clusters.
Yeah, because again, the global clusters were forming when our galaxy was still just forming. There was much more gas available back then. So you were able to basically take all of the gas that went in to form the galaxy and form global clusters along the way. Plus, all of the low mass global clusters that might have formed back then would have since dissolved also. So you're only left with these most massive ones. Right now there's just not as much gas to form these open clusters. Thank you.
Is there a red star that blue stars in general?
So most stars are red stars. Most stars are incredibly low mass. Our sun is kind of in between. It's a yellow star, but most stars would be red.
What would happen if two global clusters were right next to each other in the middle? If they were close enough to be an open cluster, would you consider that an open cluster?
No, I mean, you still have distinction based on their age. So if they look like this, they would be two global clusters. But rather, if they are very close to one another, close enough to interact, well, that could disrupt things for a while. For the most part, the stars will be able to pass through the cluster, because even in these clusters, most of the space will be empty. So stars are likely to collide. But maybe they would either pass through, or maybe after a while they would settle into a much larger cluster. Yes. Sorry, I didn't get you.
So this, she's asking about what stars are next? Yeah, they're all the.
Yeah, so I mean, there are many other things that we do have in the galaxy. We do have gas, we do have dust, which is basically tiny, when spheres of what we have on Earth, but it's much smaller, and there will be other planets. There's also this thing called dark matter, which we don't really know what it is, but it's just everywhere throughout the galaxy. But for the most part, what we think of star matter is basically the star. I see.
In quantum different constellations?
So what we refer to as an installation is basically a group of stars in the same region of the sky, but most of them wouldn't necessarily be at the same distance. They're just very bright stars that we are making in patterns. Now, so for most part, the constellations are unrelated stars. There are two exceptions. For example, Orion, as I showed before, most of these stars that you can see with the naked eye that are very bright are actually related to one another, because they are formed in the Orion complex. And also Ursa Major, the Big Bear, the 7 stars that form the Dipper also are forming a moving group. That is, all stars there are also moving in this direction. So these are two exceptions, because they are both fairly big and fairly bright and fairly close to us. For the most part, you would see star clusters being only a few degrees in size and smaller, depending on how far away they are. So most of them would appear as constellations in the next pair.
So they may disappear at one point?
Well, all stars will eventually die out, but yeah, the clusters would also eventually dissolve. Yeah.
We're mentioning dissolve as time goes on, the clusters start to evolve and move away. Is there any kind of indication of the dynamics that cause them to evolve rather than attract one another gravitationally?
Remember, there is not massive enough to hold together over a long period of time, and as the clusters are orbiting around the galaxy, eventually they will encounter, for example, a massive electron cloud or a group collection of stars that are over here, and one of these stars might just feel a slightly stronger pull towards this other region, and that will slightly change its velocity, not by a whole lot, but all these kicks will eventually add up over time, and the star will just drift away. Yes.
Does dark matter like help us get through our day on Earth?
What do you mean gets through?
Except for like making the universe go around.
What dark matter does is basically adds up an extra mass to our galaxy, but it doesn't really interact with stars or the planet all that much. it's just there. It affects how fast the stars are moving on the outskirts of our galaxy than if we didn't have all the dark matter, but for the most part, we don't really interact with it.
So the sun makes gravity to keep our planets in line.
Mhm.
What if the stars are so far away, then what makes them group together?
No, they just form very closely together, from the same cloud of gas. The cloud was initially just very cold, so, the internal motions within the cloud weren't enough to prevent the gas from collapsing. But then eventually it's able to form stars. Many of the stars would fly away, but sometimes you might have such a denser core within a cloud that ends up as a star.